Now let's see the concept of structure of page table. Okay, here there are three techniques we will use: hierarchical paging, hashed paging, and inverted paging. Okay, so hierarchical paging is a multi-level paging technique. Okay, so let's see what we are doing here. Most of the modern operating system, they use they support the logical address space up to 2 to the power of 32 to 2 to the power of 64. That means 2 to the power of 32 means 4 GB and above. Okay, they can support 4 GB and above logical address space. What is logical address space? The size of the process. Okay, so we have seen an example with 4 GB. Okay, with 4 GB there will be the process size. Okay, and what is the page size? In the previous video we have seen it. Let's recap this particular video. Okay, so let's take a scenario of hierarchical paging. First one, the logical address space is 32-bit. That means 4 GB. The size of the process equal to 4 GB. So total number of bits required is 32. Okay, and we have seen a page size that is equals to our frame size, that is 12-bit. That is 4 KB. So in 32-bit we have seen that 12-bit is offset, that is our page size, and remaining 20 bits are page numbers. Okay, so with this particular 20 bits we can create 2 to the power of 20 page entries. Okay, 2 to the power of 20 page entries. But to enter some particular thing, that means this particular page entry, page number consisting of the frame number where it will be located. Assume that the size of the each page entry is 4 bytes. Okay, then the total number of pages will be 2 to the power of 20 into 4 bytes. That will give you 2 to the power of 22 bytes. Okay, 22 bytes, that will be our 4 MB. Now we compare the page size to the power of 12 and size of the page table to the power of 22, which is the size of the page table is more than the size of the page, that is size of the frame, so that the entire page table is not going to fit in one particular frame in the main memory. Okay, so what we need to do, we need to create one more page table so that it can point to some of the entries in the page table. Okay, so that's why what we did, we created we calculated some particular values, that is page table size is 4 MB. So again we need to divide this particular page table into one more page table. Okay, that is 2 to the power of 22 by 2 to the power of 12. We will get 2 to the power of 10 entries of outer page table. So this particular 20 bits of page table will be divided into 10 plus 10. Okay, so actual page table consisting of 2 to the power of 20 entries, but now the outer page table consisting of 2 to the power of 10 entries, and inner page, it is pointing to actual page table that consisting of 2 to the power of 20 entries. Okay, now here there are two levels are there. The page table is divided into one more page table, divided into one more page table. This is called two level paging. This is called two level paging. Okay, so the technique that we are using here is, because we are unable to, the page table size is more than the page size, we need to split that particular thing. We need to create one more page table that can point to the page table, original page table. So it requires two level. It requires two level. That means in order to get the actual memory location, first you need to memory location. First, you need to refer to outer page table. There will be one memory reference. Outer page table points to inner page table. There is one more one page reference, and inner page table consisting of that particular frame number, and it will go to the original frame and finds that particular byte. Okay, so if a logical address is given, it will take minimum, in two level paging, it will take minimum 1, 2, 3 memory references. Okay, it will take 3 memory references. Okay, so this is called two level paging that can support 32-bit logical address space, that is process size equal to 4 GB. But the problem with two level paging is, this particular two level paging, okay, or hierarchical paging, is not support 2 to the power of 64-bit. Okay, so what is the problem with this one? If we take 64-bit process size, if we take 64-bit process size, that is the size of the process will be 2 to the power of 64 bytes. 2 to the power of 64 bytes. Okay, So this will create more than two level paging, because if you see this particular thing, okay, so as we take the same page size 2 to the power of 12, okay, so if from 64, from 64 bit, okay, if we take page size that is 12 bits, then the number of page table entries will be 52 bits. The leftover is 52 bits. So total number of pages will be 2 to the power of 52, which is a very large number. See, even 2 to the power 32, we have taken 1 million entries. And remember, it is 3 times more than that particular 1 million entries. Okay, so it is 2 to the power of 52. So if we divide this again, because the size is 4 KB, okay, if we divide this again, the inner page table consisting of 10 bits left, okay, this 52 will be divided into 42 plus 10, and 42 is also a large number, okay. Then this particular 42 we can divide it into again 32 plus 10, and 32 itself is a big number, so it will be 22 10 and 12 10. So this will leads to how many? 1 2 3 4 level, okay, leads to 4 level paging or 5 level paging, okay. So creating a page table for a page table and creating that particular page table to one more page table creates a lot of page tables, okay, and it will take so many memory references for one particular logical address. If you take so many memory references, that will be a time taking process, okay. So this particular hierarchical paging, we can say that it is not going to be suitable for more than, that is, system with 64 bit logical address space, that is system with 2 to the power of 64 bytes, to the power of 64 bytes. So we need to take one more page table technique, that is hash paging, okay, hashed paging.